First, let me start with saying big thanks to Gediminas and his team for organization of our meeting, and also giving me opportunity to say and tell you about our work. I will talk about generation of spin squeezing in a Hubbard system, but here this Hubbard system will also simulate Heisenberg spin chain with nearest neighbors interaction. So let me start with presenting a team. So this work was done in collaboration with Gediminas group. So here's a Gediminas. Giedrus, he was involved in the work, Marzena, and also Domantas. And from Warsaw, that's Tanasu, who is a PhD student, and Marcin Płodzień, who now is in Barcelona in NICFO. Also, I mentioned here about Alice because I will mention about our previous work, but the team which was working on spin squeezing in Heisenberg spin chain is a Gediminas team and also a team from Warsaw. So let me start with motivation, or just saying a few words. What is it about? Spin squeezing in spin chain. So the main motivation for our work is to find a way to generate regular arrangement of atoms, and we will focus on atoms, ultra-cold atoms in optical lattice in the Mott insulating phase, in the Mott regime, where all atoms share some non-trivial quantum correlations that give rise to spin squeezing and entanglement. So that's our goal, which could be useful for some quantum technological task. Spin squeezing was already generated in bimodal and spinor Bose-Einstein condensate. And here I just have a screenshot of various experimental results, many of them, in 2010 by a group of Philipp Rothlein in bimodal condensate, also by a group of Oberthaler. There is also another beautiful work, experimental work on spin kinematic squeezing by Chapman group. We have also some quite recent work about generation of Bell correlations in Bose-Einstein condensate. However, all of these beautiful experiments, they use atoms in two spatial modes, so bimodal Bose-Einstein condensate or spin-on condensates. These beautiful and pioneering experiments utilize atom-atom collision or atom-light interactions in cavity setup to generate squeezing. However, these platforms do not very weakly support single atom or single spin addressing and manipulations, which sometimes are required by some proposals in quantum technological task. That's why there is increasing interest in generation of spin squeezing in such a platforms that allows individual addressing of individual spins or atoms, also manipulation. It is not simple in spins chains because typically generation of many-body entanglement and generation of spin squeezing requires all-to-all connection. So each single atoms, each single spin interact with everybody, which sometimes is not very easy to achieve in spin chains. So we start our study a very long time ago. First proposals was about generation of spin squeezing with two component bosons in optical lattice in superfluid regime. So it is in this regime when tunneling dominates over interaction, so individual atoms could easily interact each other and also via interactions establish squeezing and entanglement. So we propose, with Alice Sinatra, we propose such a method to generate squeezing in the superfluid regime, and then raise the lattice high and put the system adiabatically in the Mott regime to store in the Mott regime squeezing. However, that was in this regime of parameters where lattice was very weak, and also one could think about the atoms that they are undistinguishable. So we asked the question, what would be the mechanism exactly in the mode insulated regime where atoms are distinguishable by the lattice site? Also, we thought how it would be with fermions, and what would be the mechanism for generation of such a squeezing and also entanglement between individual spins. So that's our story started, and we, with Gediminas and his team, we started to work on that. So first, let me remind you what are the spin squeezing and spin protocols we have in mind. So starting about spin squeezing, we need to explain what is a spin. So usually we think about two-level atom with two internal states, up and down, which can be thought and visualized on the Bloch sphere when the state of the atom is just like a point somewhere parameterized by two angles. This is by us described by creation annihilation operator and also spin rising, lowering operators using Schwinger representation. So with each such a single two-level atom, one can associate a spin. And then we are thinking about the collection of such atoms and atoms. So collective spin would be a sum over the individual spins. So we have individual spins, and then we produce a collective one which is large. And also we can thought about this in terms of the Bloch sphere, and large spin can be parameterized and visualized on this Bloch sphere. What is this? Now I explain what is this spin. We have in mind pseudo spin squeezing. From the quantum mechanics, we know that the quantum fluctuations of two dynamical variables usually satisfy such an uncertainty principle. When the variation of one product of variation of two variables has to be larger than the commutator between them. Usually for the coherent state, this variation is equally distributed. However, so it's for the coherent state, and here is visualization of such a state on the Bloch sphere. So we have equally distributed variation of the spin components. However, sometimes there are such states for which one of these variants is lower at the expense of the larger second variance, and these states are squeeze states, and because we are talking about the spin operators, we call them spin squeeze states. So here's a visualization of such a state on the Bloch sphere. We quantify the level of squeezing by using spin squeezing parameter. It should be thought in this way that it is the smallest variance in the plane which is orthogonal to the direction of the spin. Yes, so we have some direction of spin, we have plane which is orthogonal, and we are looking for the minimal variance in this plane. So it is here, and it is normalized with respect to the value for the coherent state. So it is 1 for the coherent state. And this spin squeezing parameter has such a interpretation that it is useful. It can say how the spin is squeezed, because if it is smaller than 1, it means that the state is spin squeezed. Also, it has interpretation such that the state is entangled when the spin squeezing parameter is smaller than 1, and also these states could be useful for Ramsey spectroscopy measurements. To generate squeezing, we use a dynamical protocol. One starts with the coherent state and then use unitary evolution to generate squeezing. But this unitary evolution should be with some kind of special Hamiltonians. So here is a plotted the dynamics of spin squeezing parameter in time. So it is 1 in the beginning. Then if the Hamiltonians, when chosen, it goes down and goes up. So there are two families which are the most popular in the literature. One family of the Hamiltonian is called one-axis twisting, which is like SZ to 2, and the best level of squeezing at the minima scales with the number of atoms like n to the minus 2/3. So because it is scales with the number of atoms, we say it is a scalable spin squeezing. Another family of Hamiltonians is called two-axis center twisting, and it's like sz squared minus sx squared, and the best squeezing scales like 1 over n, and it is like Heisenberg limited precision with such a states. So here's one important information for the mathematical description. Usually we start with the evolution with the coherent state, spin coherent state. We can think about this spin coherent state as a state which polarized state when all atoms are in the upper state and then rotated somewhere on the Bloch sphere, and it can be parameterized right in the Dix state basis. It is a spin basis for the maximal spin and with some magnetization. Then we use unitary evolution and calculate some expectation values. So as I said, we are interested in generation of squeezing in ultra-cold atoms in optical lattices. So usually this system can be described by Hubbard model, which is written here. When at very low temperatures, when we have exactly 1 atom per lattice side, under the single band, Bloch band, and also tie binding approximation. So what we have a tunneling term, which describes tunneling between the neighbor lattice sides, also interactions. So depending if we are dealing with bosons or fermions, interactions can be a little bit different. So for fermions, only interactions between different species up and down can exist. This on-site interaction is 0. It is in opposite with boson when we have non-zero on-site interactions. In the strongly interacting regime, when the tunneling is very weak and interaction dominates, this Hubbard model simulates Heisenberg model, which is written here. And depending of if there are bosons or fermions, it can be isotropic or anisotropic. So for example, this delta says the anisotropy. For fermions, delta is always 1, and we have a plus in the front. So it favors antiferromagnetic ordering for the ground states. While for bosons, in general, delta doesn't have to be 1. However, for rubidium atoms, we have scattering lengths which are very close to each other, and this delta is almost 1. So we could say that we have full isotropy for fermions and also for rubidium atoms when delta is 1. And from now, we only deal with this case when delta is 1. So we want to generate squeezing using a dynamical protocol in this system. So to understand how it works, we need to look on the Eigen system of Heisenberg isotropic model. So we have, it is written here in this symbolic way. So ground state, there are Dix states. So there are these states for collective spin. Yes, so we have this polar spin, which can also be rotated for any magnetization. Next, higher energies are spin wave states. Also, they are called magnon, single magnon excitations. And states are written here. So it is a superposition of such a polarized states when one of the spin is flipped with different amplitudes, and they have such energy. Next, above, there are two magnon excitation when we have two spin flipped, superposition of two flipped spins with some amplitudes, different amplitudes, and we have just addition of the energies with different parameters q, which are quasi-momenta here, and so on. We have 3 magnon excitation, 4, and we can go further. As I said, the Dix states, which are here in the bottom, are spin states in this sense that they are eigenstate of S squared and Sz. Also, single magnon states, spin wave states, are spin states. They are eigenstates of S22 and Sz. So when we start with our initial state, which I said it is a polarized state rotated, it can be written in terms of in the basis spin Dix basis for the maximal spin. We could see that there is no dynamics of this initial state with our Hamiltonian. Nothing is changed. So it is not possible to generate anything, even any rotation. So now we found the solution for that. Our idea was to, for generation of squeezing in this system, it was to add additional term, which is a spin flip coupling term. So when you look at that, it is a flipping of spin on-site flipping with some amplitude, which depends on J. J here means position of spin on a lattice. It can be simulated by off-resonant Raman Laysen coupling of these two internal states with fermions and also with bosons in optical lattice. And here is a sketch of such a setup. So here in the middle we have our system. Fermions or bosons can be also bosons in optical lattice. So we consider very weak tunneling, strong interactions, and also in addition this spin flip coupling. So how it is possible to generate anything with this spin flip coupling? So I wrote it once more. As I said, action of our Heisenberg model on initial coherent state does nothing, which is here. So when we act spin flip coupling once on such a Dix state, it produces a sum of two states, which are nothing else as a spin wave states with opposite quasi-momenta. So we go from the Dix sector to spin wave sector. When we act twice spin flip coupling on our Dix states, it produces 4 states, 2 Magnon states. So we go from Dix sector to 2 Magnon sector, or from 1 Magnon sector to 2 Magnon sector, and so on. So in the using unitary evolution operator with strong coupling, the population is transferred from the Dix sector to everywhere. So we lose a notion of spin, everything is smeared out. However, if the coupling is very weak, it is possible to keep the dynamics very close to the Dix sector. And it is the mechanism responsible for generation of squeezing in our system. So when one considers the coupling, spin flip coupling, which is very weak as compared to the Heisenberg energy, one could use the perturbative analysis to find what is an effective Hamiltonian, but only within Dix sector, very close here. So if the coupling is very weak, we consider the processes which go to the 1 Magnon excitation and back. So here is a general formula for such a effective Hamiltonian in the matrix representation and matrix elements. So we have some diagonal matrix elements and also off diagonal. And when one write it in terms of operators, one could find that effective Hamiltonian, which describes dynamic in this Dix sector, is SZ22. SZ here is a collective spin operator. So it is this famous one-axis twisting model. And the direction of axis depends on the phase, which is parameter of the coupling, spin flip coupling. So if the phase is pi, it is Sx squared. If the phase is not pi, it is Sz squared. So we found also energy and time scale analytically. And this effective description is valid only in the perturbative regime. It means when the coupling strength, omega, is much smaller than JSE, which is set by the energy of Heisenberg model, which is multiplied by some parameter, which also depends on the phase here. So what is the mechanism? Because we don't have directly interactions between elementary spin. So what is the mechanism for generation of spin squeezing? So as I said initially, we have something which is like a polar state, ferromagnetic state, and then we add very weak coupling, which means that we excite a pair of magnons, or we excite a pair of spin wave states, spin waves with opposite quasi-momenta, and these spin waves extend over the entire system and allows individual spins to correlate. That's the general mechanism. Here is a comparison of exact many-body numerical simulations with our analytical prediction for this effective model. So what is plotted is this spin squeezing parameter versus time. And please look on these orange points, which are here. They are for a spin system, which is Heisenberg model. Solid line is for our effective model only in the Dicke sector, so this larger spin sector. And Fermi-Hubbard model, this original one, is marked by green. And a part of the smallest phase, in any other cases, they perfectly overlap. Also, we check how the best squeezing, so it is at the minima, changes with number of atoms, number of spins, and we could see also perfect agreement between our numerics and analytics, and it is only in this perturbative regime. What we notice here, we also, because the theory was made for periodic boundary conditions, so we wanted to check what is the effect of boundary conditions, and it is marked here by open points. And we notice that boundary changes the time scale for the largest phase, but also one could see some quantitative difference in the behavior. So that was a reason why we also look much more carefully on the effect of open boundary conditions on the spin squeezing dynamics, and it is now available here on arXiv. So to do this, we need to back to the definition of our spin wave states for open boundary conditions. So we construct and develop spin wave theory for open boundary conditions. So what we could see, we could see difference in the wave function of spin wave states. It is not the exponential plane wave, but now it is given by cosinus function, and a small change in the energy. So with this, we could also use perturbative analysis to find effective Hamiltonian in Dicke effect sector, and we could see a huge difference. So we add this to the Heisenberg model for open boundary conditions. We add spin-free coupling, and in addition, there is a global offset phase, which is psi0 here. It was necessary to add it. With this, in the weakly coupling regime, you could show that the effective Hamiltonian has this form. So there are many, many terms, not only sz squared or sx squared, but also there are some linear terms, which this effective Hamiltonian for a specific value of the offset phase simplifies to this form, which is still not very nice. Yes, it's quite complicated. So when we analyze the limit for some concrete values of the phases, for example, on phase is pi, we could recover SYZ squared model, which is one-axis twisting, and indeed the time scale is, energy scale is 4 times larger, so it means that time scale is shorter 4 times. And also we could see a different, it's like non-isotropic two-axis counter-twisting model when the phase is not pi, it is just 2 pi over n times integer, small n is integer. So indeed, we could see in this case that the effective model changes. So what is the difference in this mechanism between periodic boundary conditions and open boundary conditions? So just to remind, for periodic boundary conditions, we had excitation of pair of spin wave states, which leads to this simplified model, one-axis twisting model for Dicke sector, while for the open boundary conditions, we have excitations of all spin wave states for all quasi-momentum. So that leads to the difference in the effective model. So what we have learned here, we could show that twisting dynamics can be simulated with Heisenberg spin chain, when one with a weak coupling to the spin wave states. we show that this effect can be induced by atom-light coupling, but actually it is not necessary to be atom-light coupling. Important is that the coupling is position-dependent, so it can be another form of position-dependent coupling. It can be considered for both bosons in optical lattice in the Mott regime and also for fermions in optical lattice in the Mott regime. So thank you very much for your attention.